Okay, so last class we saw the general structure of the periodic table, the different groups, and how the group number is basically telling us about what? What's the group number telling us? Hera? What information do you get when I tell you that certain element is in group 2? What immediately comes to your head? How many? 2, right? So group 17? 7. So things like that. So group number gives you the information about the number of valence electrons. Extremely important concept, because the number of valence electrons are most important when it comes to reactions, right? Because chemical reaction is just the transfer of valence electrons, either coming in, going out, things like that, okay? We also saw that different groups might have different names. Group 1A is called alkali metals, group 2 is called alkaline earth metals, and you see the names, these are all metals. Like, so basically on the left hand side, which is the S block, we have the metals there. Then the P block elements have both metals and non-metals. So 18th group is called noble gas, halogen 17, 16 is chalcogen, then nicogens 15th, 14th, 13th, things like that. Then we have the inner transition, we have the transition elements, which is the D block, right? We have 10 groups in that. And then we have the inner transition elements, which is the F block elements. We have the actinides, lanthanides in the F block elements, okay? So those were the general architecture. There are horizontal rows in the periodic table, and what do they correspond to? Horizontal rows, what do they correspond to? The number of shells, right? So like if you are in period 3, or the horizontal rows are called periods, if you are in period 3, you know for sure that all the elements in that particular period have 3 shells. Okay, that's very important. So within the groups and the periods, you get really critical information. Okay, so we understood that. We saw electronic configuration, and how electronic configuration gives us information about the valence electrons, and that will connect to the periodic properties today. So there might be some seemingly, and in India we call it exceptions. Do you use the same word in here when you are trying to explain some odd properties that are not? So exceptions. So we'll see that exceptions are not really exceptions. They're exceptions to the rule that people have created. That doesn't have to be exceptions in nature. Nature is following a rule that we are trying to guess. So they're exceptions to your rule, and nature doesn't have to follow your rules, essentially. So I think they're not exceptions. They're exceptions to they're limitations to your understanding. And some of these can be explained with electronic configuration, and we'll see how things are better explained with electronic configuration. We also saw the 4 quantum numbers. The principal quantum number, the azimuthal quantum number. The principal quantum number tells you about the size. The more you go, the more size, the bigger it becomes. Like, so if you have a 5th period, we'll have all elements in the 5th period will have the principal quantum number of 5. Okay. Now you also saw azimuthal quantum number, which gave you information about the shape. S orbital has the azimuthal quantum number of 0, P has 1, D has 2, and F has 3. So these gave you information about the shape. So S orbital is spherical in shape. It could be a solid sphere, as in 1s. It could be a hollow sphere, as in 2s, 3s, 4s. Okay. Then we had the P orbitals, which were dumbbells. It's like a balloon. If you pinch it in the middle, the shape that you can imagine. And p orbital can be oriented in three ways. One along the x-axis, one along the y-axis, and one along the z-axis, right? So therefore, the p orbital have three orientations, and therefore, it has three magnetic quantum numbers. So the magnetic quantum numbers give you information about the shape, the orientation, right? So P has three orientations, and therefore it has three subshells. The p orbitals, there are three boxes. Those three will give you information about the magnetic quantum number. And the magnetic quantum numbers goes from plus L to minus L. So for p orbital, whose L is 1, for p orbital, the azimuthal quantum number is 1. So the magnetic quantum number for p will be minus 1, 0, and plus 1. For the d orbital, the azimuthal quantum number is what? What is the magnetic quantum number of, the azimuthal quantum number of d? It is 2, right? Hunter, discrepancies? Okay. So when you have the azimuthal quantum number as 2, then the magnetic quantum number can go from minus 2, minus 1, 0, plus 1, and plus 2. So 5 in total. So 5 orientations. So 5 types of d orbitals. They are dxy, dyz, dxz, dx square minus y square, dz square. We'll look at, so for now, just think that there are 5 orientations or 5 types of d orbitals. Okay, 3 of these, the dxy, dyz, and dxz, are similar, and there are 2 dissimilar ones, dx square minus y square and dz square, which at this point in our discourse is not important. So I'm not going into drawing that, but you are welcome to find that out, go through your chemistry 1 lectures and revise those concepts. When time comes in crystal field theory, if I'm able to reach that, then I'll discuss more about these different types of d orbitals and how they'll become important. Okay. In that context, we also saw the Pauli's exclusion principle, which says that no 2 electrons in an atom can have same set of 4 quantum numbers. So every electron in an atom will have a very unique set of 4 quantum numbers. 3 can match, 2 can match, but 4 cannot. Okay? So there might be a few questions in your problem sets related to that. Okay, so for today, let's understand periodic properties. Yes?
Before we continue, can you do an example for the quantum numbers?
Sure.
I think last time we did sodium. Can you revisit that?
We can do sodium, we can do anything else. So there was this practice problem set, right? Let's do an example from that. Do you have that practice problem set? Melissa, you had that, right? If you had it, yeah. Which one do you want? We can do this. Let's do a couple of examples, okay? So question 15 on the practice problem set is this. Which of the following sets of quantum numbers represent an impossible arrangement? Take a minute, and I'm not going to write this. So let's do 15, and which one do you want to do, Hunter?
I was just going to ask if you could do, like whenever we are figuring out the quantum number the magnetic orientation.
Okay, so
Something similar.
is it sodium is okay, or do you want to do iron?
I mean, it doesn't
or-
matter. I'm just
Yeah,
trying to see if we can do one.
let's do iron. So tell me the configuration, the electronic configuration. Who wants to try for iron?
Is it 1s2?
I'll let the undergrads first try.
One S2, 2S2, 2P6, 3S2, 3P6, and 4S2.
How many?
And 3D6.
Venus? Is it okay?
Would you fill the d orbital first?
Why?
Mistaken?
Why would you fill the d orbital first?
Because it has a lower principal quantum number?
So,
But it's correctly, it's
It's correctly
fully
written.
filled.
Yeah. But I suppose that's just like a technicality, right? As far as how the electrons fill it. But that's the correct way to write it. So, I mean, the last electrons go into the s orbital.
no,
Or, I'm sorry, the d orbital.
the d.
But that's the correct way to write it.
So you want to write it 4s2 after 3d6? That's what you're asking?
That's how I did it. But I
And that's fine, but how did you fill it? Which one did get filled first?
S2.
4s.
4s2.
Right.
I'm sorry.
So 2 is just the number. So 4s got filled first. Is there any doubt with that?
No.
Okay. So you just wanted to write this 4s this side.
Yeah,
But you know that the 4s got filled first.
I do.
Okay. Yeah, then it's okay. Because that's what Lauren did the first time we did it. Do you remember? You gave me the electronic configuration of lead in the correct order. But for people like me who just follow that balloon system, it's easier for me because I know that the balloon is hitting 4s first and then the 3D. And why is that? Which rule governs which of these are getting filled first? What's that rule? What's the name of that rule? It's just a simple. So Hund's rule, that is maximum multiplicity, is the Aufbau's principle, which tells that the filling in of the orbital is based on the energy, right? And the energy is what? N plus L. So what is N plus L for 4s2? And what's N plus L for 3d6?
Isn't it 4 for that one?
3 for the 3DS.
For 3D?
Or 3, yeah, for the N on 3DS.
Yeah, plus? So D, what's the L for D?
Oh,
0, 1, 2, 3, 2, right? So this is 5.
and then S is 0.
0, and that is why 4. And that is why this got filled first. Because the N plus L is lower for 4s than for 3D. Jocelyn, does it make sense? Agreed? Okay. So this is the configuration. Now, if we are, which electron, so every electron will have 4 sets of quantum numbers. Under which one do you want me to write?
4S.
4s? Okay. We'll write for multiple of them. So which one? The down or the up?
Down.
Down. So the one that came later. And we just have to go for the principal quantum number and then L,
M.
so what is the N for 4s? 4.
0. I'm sorry.
This is 0, L. M, what are the possible values of M?
Because it's, oh no, I'm sorry. It's 1. Because it's an S orbital, correct?
Right. For s orbital, now think about this really carefully. There's only one value for M associated with the s orbital. And what is that value? There's only one value, but what is that value? It can go from plus L to minus L.
So then it's just 0.
It is 0, right. Because it can go from 0, there's no plus minus, there's only one value.
Gotcha.
And what is S?
Yeah, see, that's why I was asking for a reason. I don't remember what S is. It's either, it's all, I can never differentiate if it's plus half or minus.
Let's assume it's just you can assume it just minus half or plus half. So I assume plus half and minus half. So one is clockwise and is anti-clockwise. It's a spin of the electron. So when it spins clockwise, I think it's said to be negative half, and then the anti-clockwise gets the positive half. But for our purposes, just the up arrow, just do it positive, and the down arrow negative. Yes, correct.
So if our L isn't 0 and we go to M, do we have to write like all of them?
Let's do for D. 6, okay. So when I fill the electrons and then I do this, which rule did I follow? I filled all of them and then I put the pairing. Which rule? Yes, so Hand's rule of maximum multiplicity. So you're just filling up each individual orbital first and then pairing up. Okay. Okay, which electron do we want to write the electronic configuration? The 4 quantum numbers. Yeah, I mean, there are all these electrons. All of them have 4 sets of numbers. Which one do you want to go for?
Do the one that's half filled, since we already did a full fill.
The second.
The second one? Okay, let's do for this. So we know that this is a 3d6. What's the N? It's easy. L. D. And D is?
N minus 1.
2. Sorry?
Oh, I said N minus 1.
Yeah, and this can go from, what's the M values? They can go from -2 to +2. So -2, -1, 0, +1, +2. So what's the M value? -1. M can have 5 values, possible values, right? But what is the value? The actual values of M can only go from, what are the possible values of plus L to 0?
Or minus L plus L.
Right? So it can go from +2, -2, -1, 0, 1, and 2. So there are the number of possible values of M for d orbital is 5. This is 5. But what is the actual value? You get it from here. I think that's what you're getting confused with.
But why is the actual value -1?
It is just you are giving a number to one of these boxes.
Oh, it's because we're working with
This electron.
that specific. Got it.
Yeah.
Gotcha.
If you work with this electron, the value will be 0. It's like that. Yeah.
So I have a question about the different boxes, because I understand that when we're in a shell, so like for the SP, D, or F, that's the correct kind of notation, right? Is that we're in a shell, S, P, D, or F. But whenever we're talking about the orbitals, those are the individual boxes that the electrons occupy, right?
So S is not the shell. So there's this thing. It doesn't translate very easily. But just imagine when we are talking about the periods, they're corresponding to shells. Each shell will have a certain number of orbitals, S orbital, P orbital, right? And these could be like suborbitals.
Okay.
Yeah. Okay.
It helps me understand M if I'm, saying that the orientation of this suborbital within the
Yes.
SPDF orbital is
Yes.
such.
Yes.
Then, I know.
The thing is, these are all, so the orbital concept replaced the shell concept. What I imagine, and in my head, and that gets me through the practical, serves the practical purpose, is understanding shell, orbit, shell or orbit, orbital, suborbital. That's what I think in my head. Okay. All right. So, and the S could be plus half. So this is -1 plus half. Okay. So let's go for question 15. Does everyone have this with them? Okay. So the question is, which of the following sets of quantum numbers represent an impossible arrangement? So the arrangements are 3, 2, -2 plus half, 4, 0, 0, half, 3, 2, -3, half, 5, 3, 0, half. Which of them is impossible?
What question is this?
15 from the practice problem set that I gave. They're like 2 sheets, just 2 sheets.
15 for me was the number of the electrons.
No, you're looking at the.
You're looking at the actual problem set.
Remember, it's the practice set
I
that
see.
you gave us.
Okay. My fault.
That's fine. Just tell me which of them is impossible. Okay, Tiffany says third is impossible. Who agree?
It's really the M value that stands out. the most.
Yes. So this one is not possible because this is 2. So L is 2, L is 2 for D, right? So you have a D orbital, which L value is 2. So these M values can go from -2, -1, 0, +1, and +2. It does not have a -3. Okay, that's why. So this is impossible. Which shell is this?
D.
So this is 3,
Oh, sorry. Just kidding.
this is 3D, right? This is 3D, and an M of -2, that means it's filling here, and a plus half, something like this. Can you imagine which, if this is the last electron filling in, which atom is this? If imagine that 3D1 is the last electron coming in, what is the atomic number of that element, and what element is that?
It's 21.
It is 21, correct. It's scandium. So memory serves its purpose sometimes, right? So I remember that 21 is scandium, and that's why it was easy. Same for this. What's this?
It's in 4S.
Based on this, what do you say? Is it 1 or 2? 1. What is 4s1? Okay, let's do this. So 4s1, which group is that? 1 group. So alkali metals.
Whatever 9
Huh?
is whatever 9
Okay, let's do it two ways. Let's do it two ways. So you have 4s1. First, we know that this is 4th period, group 1. So we can go through that. So 4th period, group 1. So if I know who knows? Does anyone remember?
It's an alkaline.
It is, because it's group 1. So this is 1, 2, 3, 4. So it's potassium, right? And then, if it is 4s1, can you find out the atomic number? Because if it is 4s1, you also know what went before that. So you can go through the atomic number route. Can you find out what went before 4s1? You have something here. See it from here. How many were these? What was this? What is this? 18 plus 1, 19, right? So it is potassium, 2 ways. Does this make sense? So this is not possible. Tell me this. Think. You have to give me the element. If you cannot give me the element, at least give me the atomic number. Because atomic number is as good as the element, because the element is the atomic number, right? So what's the Z? And I'll see if I can figure this out with the atomic number or not.
Well, it's in the F orbital, right? Because N is equal to 5.
Yes, it's the F. So definitely I'm not going to, because I've forgotten the F orbitals.
Yeah, I couldn't tell you. I'd have to do the...
So this is F. What F? What does this tell you?
That it's in the 4th suborbital.
So this is -3, -2, -1, 0, 1, 2, 3. So it has to be something like this. It cannot be this, because if it has to be -half. So if it was -half, then all of them have to be half filled first, and then when you were refilling it, then it would have been filled. Does that make sense? Who is confused? This is for +half, and for -half, this is the -half configuration. This is -half. And this is +half. Who has doubts? No one? Good. So this is 5F what? How many electrons? 4. So this is 5F4. You just have to find out how many electrons went before that 5F4. Okay?
When we do N plus L, what are we finding?
It's the energy.
Energy, okay.
Yeah, N plus L is the energy. I mean, it's a proxy for the energy. And what if N plus L is the same? For example, 3p and 4s have the same N plus Ls. Isn't it? What's the n plus L for 3p?